Engineering. Today we're going to work on this LeetCode problem, constructing string from a binary tree. So let's start from the problem that given the root of a binary tree, we are asked to construct a string consisting of parentheses and integers from a binary tree with the pre-order traversal and return it. We need to omit all the empty parentheses pairs that do not affect the one-to-one mapping relationship between the string and the original binary tree. So this is an example of it. Input root 1, 2, 3, 4, and then the output is 1, 2, 4, 3. Okay, and look at the parentheses here. So 1 has the parenthesis for all things that it being traverses on the left child, and another parenthesis set for the right child. Then on the 2, it's the same. It has the parenthesis for the left child. But there is nothing for the right child, so there is no parenthesis at all here. So the right child for the number 2 can be omitted because it doesn't affect the representation meaning of the trees. Okay, so that's basically what it is, an example of what the problem asking us to do. Let's see example number 2 here. This is an example that signifies when an empty parenthesis should be drawn out. So 1, 2, 3, right? 1 has a parenthesis for the left child, and the left child, which is having the subparent of 2, has no left children, so it has an empty parenthesis here. Then the parenthesis for its right children, the 4. So this is where the empty parenthesis has to be kept intact. So that's also what a pre-order traversal is. Basically, it's trying to go to the left all the way, then to the right of it, go up, then right. Okay. So that's basically we already understand the problem about what it means about the parentheses. That's one of the unique non-trivial things about this problem. The other part of the problem is about the pre-order traversal itself. Okay, now that we understand those two, what we need to do here is actually to express it in terms of codes. Okay, so what happened here is it means we got here a root, which is an optional tree node. So basically, we got a node with the value left and right. So that's basically the input representations of the problem. So for example, if this is the case, this is the initial root node that we will got. So how do we going to do this? Of course, for this one, there is nothing significantly need to be think of, I think. What important here is to be able to express it in format of code. Let's start it. So basically, when we get a node, we will start storing it to be printed out later. In order to do this, because I'm using Python, what I will do here is I will prepare an array that will store all the things that I will print out in the future. Because what happens is what we're going to print, we're going to get it little by little, bits by bits, as we traverse the nodes. So more or less this is what we're going to have. And at the end, we're going to join it all into a single string. Okay. So now that we have it, that's the part of it. Another part is how do we do this traversal? We will do this traversal by having some kind of a stack. We can use a stack here. Okay. The stack will initially have the root. Basically, the stack will contains all the nodes or other things which later on will be the parentheses, right? Because that's, if you notice, this is the what non-trivial with the normal pre-order traversal is about how you shoot things on how to print out the parentheses. So later on, we will actually put the decision when to print a parenthesis into the stack too. Okay, so we got the stack root. Then what happened next is actually we will keep on while there is something in the stack. Okay, then the node in focus will be the stack that we pop. Okay, and what happened here is we need to do something, which is basically once we imagine this is the root. When we pop it, we got the root. Then what is important from it is we need to print the value, right? So what happened here is we can append it to the list which later on we're going to join as the printed string. For this case, it means it will be the node.file following this structure format. After that, after we print, the next is about thinking about the children, which is the left children and the right children. And the print order will be the left first, then the right. So it means we have, because this is a stack, you have to think it in a reverse way. It means you actually have to add in the right child first, because later when we pop will pop the last entry. So the first one that you want to print next should be the last. That's why we do it in reverse. Because we want to print the left first, we put into the stack the right one first. So stack.append the node.right. Okay, and then that will be what it is. The next one is to append the left. Now, there is something here that we need to be aware of. It could be that it doesn't have any right children or any left children, right? What happened then? If it is the right children, if it doesn't exist, then we simply don't want to print it, because the right in the pre-order traversal usually always be the last one. And if it is the last one and it is empty, we don't want to print out empty parentheses, right? So in that case, we need to cover this with some if check. If not.right is not none, that's when we're going to append it. Okay, now that's about the right part. Then how about the left part? The left part, we also going to only append the node if there is a left one. But one thing to be noticed here, which is explicitly described as the example, we do want to print out empty parentheses even if the left one is null, if the right one is not none, right? It means it's actually have to be here. So when the right one is not none, we actually want to print the left one. If not.left is none, then we do want to add into the stack, which is what is to be printed next, the empty parenthesis. This is the only case where empty parentheses happen actually, when the right exists but the left doesn't exist. Otherwise, empty parentheses should never be exist at all. And for programming, usually you should put in some sort of equivalent constant, but because Python doesn't have constant, I'll just use some global variable to represent the empty parentheses. This is helpful in real programming when you are maintaining it, because it will help the IDE to give you this consistent things to write when you write the code for those kind of easily mistaken constant string values. Simple typo, it can break your code. So it's better to put it as a variable. And then that's about the empty parentheses. Now, how about this parenthesis here, right? How about the technique we can use to add in the parentheses is logically speaking. And for that one, actually, whenever you want to enter something, you just need to think it the same way. Like how we think that we want to put it in reverse, what we want to print first will be the one to be the last that we add in. So in that case, let's prepare the left parenthesis and the right parenthesis variable. Okay, so what happened here is whenever we want to add the right any kind of node, actually we will need to append the parentheses in reverse. So if the first one to be printed is the left, it means we have to write put in the right parenthesis first, which is the last to be picked out from the stack later on, right? Then we will also append the left parenthesis in this kind of order. The same with this node. Okay. Now we already covered adding the parentheses, adding the node, adding the empty parenthesis cases. One thing that small thing that we need to be care about is we need to convert this node.val into string, because when we do this join, everything here has to be a string. Okay. Another thing now is this node.val only doable if it is a node, but because we also add another data type, which is a pure string here into the stack, we need to cater for that. So in this case, we need to do an if check. If node in any of this, yeah, right, parentheses, then what happen is we just need to append the node directly because it's a string. Okay, so that's about it, logically speaking. So let me summarize what we are doing here. Basically, we are doing a pre-order traversal. We use stack data structure to help us traversing in a pre-order traversal, starting from the root, and then we pop the stack one by one. And what happened here is the way we embed the parentheses is by adding it as part of the stack content later on. And then that's where the two different handlings here happen, when it is the parenthesis and when it is a node. When it is a parenthesis, we simply add the string to print, and then we just skip the while to the next stack content. If it is a node, the handling is a little bit more involved, like we add in the value of the node to be printed, then we try to check the children to update our content for the stack. And then for the stack content, we need to be careful in the order that we put it in. We have to think it in reverse to what we want to print. That's why we start from the right, because we want to print the left first. We start from the right, and so on with the parentheses. We start to add into the stack the right parentheses, and then the node to be traversed further, then the left parenthesis for covering that not printing, and then there is a special case here where if the right is not none but the left is none, then we have to print an empty parenthesis set. And then the same thing is happened with the left child. After all that's said and done, we join everything that we cumulated into the list as a single string with this join command. Now let's try to test this out. And so far with this single sample test case, it works well. Now let's submit it. There you go. We've done it. Now how about the big O notation? For the big O notation, let's traverse it step by step. This one, of course, just an initialization. That is big O1, just initialization. This one, the while loop, it means it will be as many as the node, because this is traversal, right? So at the very least, because we're going to put in all the nodes, so it will be big O(n) at least towards the number of nodes. But to be noticed also, for every node, at most we more or less going to add in about 2 additional parentheses. But because the additional of parentheses here more or less grow constantly, because it's like one node will have 2 parentheses anyway, so you can think about it like this is a constant multiplication towards the end, which is between 2 or between about 2 actually, because it's always been a set of parentheses except for the parent of the root, of course. But more or less we can simplify it in big O notation as constant times n. So this is in the end still just a big O(n). And then the joining itself, it's of course depends of how it internally been done. Obviously we can think about that it is going to be a sequential glued between all the components in the array, so it will be another big O(n), right? But this is happening outside of the while loop, so it doesn't increase it. In the end, big O(n) plus big O(n) still result in big O(n). So this is a big O(n) in terms of time complexities of it. In terms of the memory, the most the stack will have, if you can imagine it throughout how pre-order traversal is, it will traverse all the way to the left. It means the most memory is about the height of the tree. And the height of the tree, of course, at the worst case, if it is everything is the left one, is a big O(n). Because here it doesn't say anything about what kind of tree input. It could just become, the worst is big O(n), the best is log n, which is when the tree is a balanced tree. So that's it about the time complexity and memory complexity. Hopefully this helps. This helps us to exercise our thinking in code. Thank you. That's it for code engineering today.